At this point, we have talked about system curves. We have talked about pump characteristics. So we're ready to go back to this example. So our scenario was we have this whole tank. There's a negligible length here. We've got this centrifugal pump. Then we have this line leading 6 meters to the right. Although you can't see it in this picture, you can see it in this picture. It goes back 8 meters. And then another elbow, it goes up 4 meters and then into the top of this liquid extractor. And we've got this control valve here. And we're going to consider a number of different positions of the control valve. So this will be set at some position and we want to investigate what happens. We are doing the more realistic version of this problem, so that was problem number 2 in this set of notes. For 3 positions of the valve, fully open, 1/2 open, 1/4 open, calculate the flow rate through the pipe in both kilograms per hour and meter cube per hour, the total head delivered by the pump, and the pump efficiency. Present your results in the form of a neat table. And then here's this interesting last thing here. Also plot the flow rate in kilograms per hour as a function of valve position expressed as a percentage of the fully open position. And that's the really interesting part of this problem. We're told the pump that we're supposed to use, and this is it. It's one that operates at 750 RPM, and here are characteristics for different impeller sizes, and we are told to use the 6-inch impeller. So I guess you could say that the pump has been chosen for us. So how do we solve this problem? Well, the first thing is we need system curves for all the valve positions that we were asked about. Well, we talked about that in the first segment of this lecture, and we know how to calculate system curves. We actually saw all the system curves. The next element is the pump characteristic. Well, we just looked at that. So what's the key idea here? As I noted in the last video segment, both the system curve and the pump characteristic is a plot which has the horizontal axis being flow rate and the vertical axis being total head. In the system curve, it's the total head that you need as a function of the flow rate. In the case of the pump characteristic, it's the total head delivered by the pump. So what you really need to do is to match the head that you need with the head provided by the pump, and you have to be at a point on that graph where you're simultaneously on the system curve, because that characterizes the dynamics of your system, and you're also on the pump characteristic because that's the pump that you're using. So long story short, how you find at a given valve position where you are is to look for the intersection, because you have to be on both curves at once, at the intersection between the system curve and the pump characteristic. So it's as easy as that, actually. So let's take a look. This picture here is for the valve 100% open, in the fully open position. Here's the system curve. We actually saw that before. Here's the pump characteristic for the impeller that we're using, the 6-inch impeller. Notice that I actually made this with an Excel spreadsheet, so I read points from the graph on the pump characteristic and put them in my Excel spreadsheet. So this is the pump characteristic that I read from the graph. And this is the point of intersection. So at this particular valve position with the pipe that I have and the pump that I have, this is where the system will be. So I read down here, it looks like the flow rate will be 136 cubic meters per hour, and the head required to move the fluid through the pipe at that flow rate looks like about 6.53 meters. And of course, you can convert the volumetric flow rate to a mass flow rate if you know the density, and that's 1.39 times 10 to the 5 kilograms per hour. So in a nutshell, for a given valve position, how do you find what the actual flow rate will be or where the system will be? You look for the intersection between the system curve and the pump characteristic, and that point of intersection, that is where the system will be. In the first video segment of this lecture, we also considered other valve positions. So for example, here is the system curve for a 50% open valve. Again, it's higher than the previous one because you need more head to pump the fluid through a more choked off valve. And the pump characteristic has not changed. Same pump, same characteristic, but the system curve has changed, so the intersection happens at a different place. In this case, reading from the graph, it looks like about 97 cubic meters per hour. And the head Yeah, about 7.7 meters. And you can convert this volumetric flow rate to a mass flow rate. That's about 0.99 times 10 to the 5 kilograms per hour. Yet another case. Third case we want to consider, what if the valve is more choked off, only 25% open, then the system curve is even higher, need even more head to force the fluid through that even more choked off valve. So the system curve has changed. Again, the pump characteristic is the same, but because the system curve has changed, the intersection happens at an even lower flow rate. This time it looks like about 64 cubic meters per hour, corresponding to this mass flow rate, and the head is even higher, 8.6 meters. So this is me here just compiling all the results that we read from those three intersections in a table for the three valve positions that we were asked about. What is the volumetric flow rate converted to a mass flow rate, and here's the head that's required. Now, about the pump efficiency, how do we get that? Well, here's the pump characteristic for that 6-inch impeller we're supposed to be using, and for the three flow rates that I got from those intersection of the pump characteristic with the three system curves, the three operating positions were this flow rate, and this flow rate. Flow rates are going down because I was choking off the floor more and more. And then just by eyeballing this graph, you can see what the efficiencies are. So for example, at this operating point, the efficiency is between 75 and 78%, following this curve and this curve, a little closer to 75%. For this operating point, I'm between the curves for 70 and 75%, and for this operating point, I'm actually slightly below 60% going by this curve. So just kind of eyeballing or interpolating by eye between those curves, this is where I got the pump efficiencies at those three operating conditions. This graph here is really interesting. I'm just plotting these results, the valve position here, and what flow rate I got here. So let's look at this curve. Really interesting. For different valve positions, I get different flow rates. These are the three results that I got. This is what you actually need to control the flow. Because in a control system, you want to maintain the flow, or maybe the flow got out of spec. And so if you want a certain flow rate, you know exactly how much open you have to have the valve. I said before that typically you want to operate around a 60% open position, so you want to operate around here. What is the flow rate there? It looks like about 108 cubic meters per hour. What is the maximum possible flow? Well, the maximum possible flow is when the valve is fully open. That number was 136 cubic meters per hour. That was one of our results. So you want to operate here at 108. The maximum possible is 136. So what is 108 divided by 136? That's actually about 80%. So that kind of justifies my generic statement that when you operate in the valve at about the 60% open position, you're actually at about 80% of the maximum possible flow rate. And that's a good place to be because you can go up by about a quarter, 25% up or down in trying to control the flow. This graph here is really interesting, and this is ultimately what you need to know. Because if you want a certain flow rate, you have to know how much open you have to have the valve. The key thing to notice here is it's not as if you control the flow by changing the RPMs on the pump. Absolutely, that's not happening. And it's not as if you have the valve at the 60% position, you get 60% of the maximum possible flow. For a given valve position, the actual flow rate is a dynamic outcome of your piping system and your centrifugal pump. And the only way to know is to actually do the math, and we've done the math. So this is a calibration curve that lets you know how you should position the valve to control the flow at what you want.